In this video, we will learn how to determine the structure of an unknown compound using data from IR, mass spec, and NMR spectroscopies. These are our three tools, and it's good to kind of just remember what they're useful for. So mass spectrometry is good for helping us figure out the chemical formula of our unknown molecule. IR spectroscopy is good for helping us find certain functional groups as being either present or absent in the molecule. And NMR is also good for identifying functional groups, but more importantly, NMR is useful for kind of fine tuning. For example, if you know the functional groups and chemical formula, NMR will help you figure out which structural isomer of those little pieces is the correct one for your unknown molecule. So let's take a second to look over the typical workflow for dealing with unknown structures. This is by no means a required path, but it is kind of generally speaking the path that people will take, right? This is all one really big puzzle, and so there's no really right way to approach this problem. This is probably the path of least resistance. So most people will start out looking at the mass spectrum of the unknown sample. And when looking at the mass spectrum, asking questions such as where is the molecular ion? Are there any M+2 signals that might tell me there are halogens or sulfurs in my molecule? Seeing, do we have any information about number of nitrogens in the molecule? And finally, can we get a rough estimate at least for the number of carbons? At this point, it's not necessary to go through and actually derive a chemical formula because the other data will give us some more information that will make our life a little easier. Next, it's helpful to look at the IR spectrum and see if the IR indicates the presence of any very obvious functional groups. So typically this will include things like anything containing a carbonyl or any functional group containing a nitrogen-hydrogen bond or an oxygen-hydrogen bond. Sometimes benzene rings are very obvious in IR spectra. And so once you figure out any of these pieces of information, it is possible to go back and update your formula, because if you see that there's a carbonyl, then definitely your formula should have an oxygen atom in it. Or if you see that your formula has some sort of NH, then that helps you figure out what's going on here with the number of nitrogens that you expected. Then it's good to go to the NMR and just look through the NMR at a kind of big picture level to see whether or not you can identify any other functional groups and whether or not you can kind of corroborate the functional groups already identified by IR spectroscopy. So here we're looking for things in both the carbon and proton NMR, but more typically in the carbon NMR, we're looking for things like, are there alkenes that we may have seen from IR? Are there things like aldehydes, right? Carbonyls, and specifically aldehydes, are interesting because they have both a carbon signal that's identifiable and a proton signal that's identifiable. Things like that. Once you do that, you can usually begin to do the work of finalizing the chemical formula that you believe the unknown structure has, because you've figured out number of carbons. Using the NMR, you can usually corroborate the number of carbons, or at least gain a little bit of info about symmetry if there are less carbon signals than you might have expected from mass spec. You can also deal with the hydrogens this way and finally get to a formula that should match, right? So the integrations that you get in your proton NMR should be consistent with what's predicted by the mass spec chemical formula. Once you have a chemical formula, then it's important to go through and always calculate what's called the degrees of unsaturation of the molecule. The formula looks like this. So the DOU is equal to 2 times the number of carbons plus just 2, plus the number of nitrogens minus number of hydrogens minus number of halogens. So here this would be fluorine, chlorine, bromine, iodine. Take all of that, divide that by 2. That will get you to this number, the degrees of unsaturation, which refers to the total of the number of rings and number of pi bonds in a molecule. So for example, a benzene molecule has 3 pi bonds and 1 ring, so the degrees of unsaturation for that should be 4. So you can go through and test that math for yourself. The degrees of unsaturation is useful because it's always an integer value. You can't have half of a ring or half of a pi bond. So if the DOU you calculate is not an integer, then that means your chemical formula is wrong, and you need to go back and figure out what was missing or extra. You can start to account for the degrees of unsaturation using some of the functional groups you may have already identified in the IR or NMR, but in the end, your structure should, of course, account for all of those degrees of unsaturation. So let's say the carbonyl takes away 1 degree. If you see an alkene, that takes another degree, etc. With this information all put together, you can start to do a little bit of fine-tuning of your functional groups. So using the identified functional groups and then their specific locations in the IR spectrum, you can sometimes identify whether there's conjugation or strain affecting that functional group, and that gives you a little bit more context to the structure. And as you do that, you can also go through and at the same time use the proton NMR, using the splitting patterns especially, to figure out where the various parts of the molecule containing hydrogens ought to be located relative to each other. This whole process is definitely going to be a big guess and check process. You have ideas on what you know, right? You know some certain fragments, but you have to go through and just kind of put them together in ways that may make sense, and then just kind of go through and always double check constantly whether or not what you came up with is consistent with everything else throughout this entire process. Right? So this general workflow may seem simple, but it can take a very long time per unknown structure, depending on the complexity of what you're dealing with. All right, let's go through and look at an example of an unknown structure determination. So here I have a set of data. At the top is the carbon-13 NMR spectrum, and right here is the proton NMR spectrum. Very bottom left here is the mass spectrum, and then right here is the IR spectrum. I know some of the font is a little bit small here, but I'll try to point out exactly what's being referred to. So we should go through and look at these various pieces and figure out what we can figure out. So from the mass spec, it looks like my molecular ion is at 86 m/z. It looks like my relative intensity of the M+1 peak is small compared to the molecular ion peak, and additionally the intensity of the M+2 peak is very small, right? So I shouldn't have any chlorines, bromines, or sulfurs. And if you look at this and take a ruler and measure this out, this comes out to be 5 or 6-ish carbons per molecule here. So the ratio is about between 1 and 2 relative intensity of the M+1 peak to 20 for the molecular ion peak. So I'm going to guess here that there are 5 or more carbons. The molecular ion is even, so should have even nitrogen numbers here. At this point, it's not necessary to go through and actually try to deduce the possibilities. It's better to get a little bit more information from the other data before coming back to the chemical formula. So now let's look at the IR here. So the IR has definitely the CH stretches, which makes sense. We have an organic molecule. But if you look at the 3000 line here, it seems like all of my stretches are to the right of that, or to a lower wave number. This suggests that we should be dealing with just sp3CHs. Right? We can put a little question mark because we're not sure. The other thing we can see is a significant stretch occurring at 1718 inverse centimeters. That's exactly in the range of a carbonyl containing functional group. Right? So we should definitely notate that. We see a carbonyl. The value here of 1718 would match a ketone that is completely unperturbed. Right? Doesn't have any conjugation or strain or anything like that. So maybe we can very tentatively say that this would be a ketone. The thing that we have to be careful of is that it could also be a different carbonyl containing functional group that does experience some of those factors, such as delocalization or strain. So we don't want to categorically rule those out yet, but right now we are thinking maybe ketone. As we go over to the NMR, a good place to start is the carbon NMR. And so what we want to do first is just figure out how many different signals there are. That will give us the minimum number of carbons that are present in our molecule, right? Because the number of signals is the number of unique carbons. So that is definitely the minimum number. There could be more if there's symmetry, but there can't be less. So there is one signal out here that's very small. This cluster right here, that's the solvent reference signal for chloroform, which is CdCl3. So we ignore these kind of, it looks like 3 equally sized peaks. We just ignore those. So we have the one on the very left there, 2, 3, 4, 5 total signals. The other thing to look for is that because we have a little bit of information in our IR that we have this carbonyl containing functional group, we should check, well, do we have that in the carbon NMR? We do have a signal for a carbon over carbonyl. Those always show up past 160 or so ppm in carbon NMR. And more specifically, this signal is right here and showing up past even 200 ppm. When that happens, that corresponds to two possibilities, either a ketone or an aldehyde. When you have, for example, an ester, the carbon-13 shift is more in this region, so below 200. Well, given those two possibilities, an easy way to distinguish these two functional groups from each other is to look for the proton that would be on the aldehyde. That shows up always in this characteristic region around 10 ppm, where almost nothing else shows up. And if we look to the proton NMR, there doesn't seem to be any signal here in the proton NMR, which suggests that we do not have an aldehyde, which by process of elimination brings us to ketone being the best choice. This matches nicely with our IR, where we thought that we might have a ketone that does not have any conjugation or strain factors affecting it. Let's keep looking at the proton NMR. So it looks like we have some signals here. There are 4 different types of proton signals, and those are in a ratio. I know you can't see the integration here, but these are coming in at a ratio of 2 hydrogens for that one, 3 hydrogens for that one, 2 for this one, and 3 for that one. So based on those integrations, then we can say that the minimum number of hydrogens in our molecule is going to be 2 to 3 to 2 to 3, so 10 total hydrogens. We can't have less than that because then we wouldn't have integer ratios or integer numbers in our ratios, but we could have more if, for example, the molecule was symmetric. So we should have 10H as one possibility. If the molecule had some symmetry in it, then we should have 20H. All right, so with all of that, this is a good time to go back to the chemical formula. We've already determined that we likely have the minimum of 5 carbons, so we see that in mass spec and in carbon NMR. We have 10 hydrogens. We also have an oxygen because we know we have a ketone. So let's go through and write that out. So we have C5 maybe, H10 maybe, and oxygen. If you go through and add up all of those atomic masses there, what you'll find is that this has 86 AMU. That's exactly what we see in our mass spec. We don't have to do any more work to see if we need more carbons or more hydrogens. Given all that, then we should calculate our degrees of unsaturation. So the DOU of this molecule is going to be equal to 2 times 5 carbons plus 2 minus 10 hydrogens divided by 2. That's all equal to 1. So we should have 1 ring or 1 pi bond in our molecule. We already know we have a pi bond from the ketone here, so we're all set in terms of degrees of unsaturation. The rest of our molecule should not have any rings. So why don't we go through and already try to build the molecule? We know we have a ketone, which already takes care of 3 carbons and the oxygen. At this point, we need to figure out where the remaining 2 carbons go, and just to make sure whether or not the splitting pattern tells us any other information. So if we go through, one thing we should keep in mind is, well, we need to know where the chemical shifts of protons near carbonyls or ketones would show up. That tends to be around 2.1 ppm. And so if I'm looking past the 2 ppm mark in the proton NMR, I see 2 signals, one for 2 hydrogens, one for 3 hydrogens. The splitting pattern of these 2 signals are a singlet for the 3 hydrogen integrated peak and a triplet for the 2 hydrogen one. And so if I go to my structure here, then it should make sense for me to put in 3 hydrogens on one side of the ketone here, because these 3 hydrogens wouldn't have any 3J coupling to any other hydrogens, which means that they would show up as a nice singlet, 3 hydrogens. This is a pattern that shows up a lot, where a methyl group will show up as the integration for 3 hydrogens. Makes sense, because methyl groups have 3 hydrogens in them. And then I must have 2 hydrogens at this position, because I had assigned this triplet here to possibly being next to the carbonyl. I know from my formula there's no other electronegative atoms. There's no other anisotropy because I have the pi bond already in my carbonyl. So the only thing that could bring a signal downfield like this has to be the ketone itself. So I have to have those gray triplet signals coming from these two hydrogens here. If it's a CH2, only two hydrogens on that carbon, then I necessarily need to attach to another carbon. This next carbon now, I have this question of, well, how many protons do I put there? Well, the splitting pattern tells me something here. These two gray hydrogens, their signals are split into a triplet, which is for two neighbors plus one, according to the n plus 1 rule. So that tells me there are two other hydrogens here. So I will put those in here. If we look at our NMR, we've already taken care of those two hydrogens signals, those three hydrogen signals. And then what we have left are a 2 hydrogen integrated signal and a 3 hydrogen integrated signal. So naturally, if we have 2 hydrogens, that's got to be this one right here. So I will go through and color code this now. 2 hydrogens, like so. The splitting pattern we see here, it's a little hard to see in the video, I know, but there are 1, 2, 3, 4, 5, 6 lines right there. I'm going to write this out as a sextet or a hextet or a sextet. If that's the case, that means that the red hydrogens should have 5 neighbors with the same J value. And if that's going to be the case, that means we have the gray ones already accounted for, 1, 2, and then we have 3 more on the other side. Right? And that makes perfect sense because the only other signals I haven't accounted for are these 3 hydrogens from this triplet. So let me go ahead and put those in. 1, 2, 3. That's those 3 hydrogens. It's a triplet. So we should just go through and double check that this last signal splitting makes sense. I see a triplet here telling me there's 2 neighbors to these blue hydrogens out here. And that looks to be the case, right? There are 2 red neighbors to the blue hydrogens. All of that then adds up to give me this molecule as my final answer for the unknown that this data represents. This is 2-pentanone. All right, let's look at another unknown. So here we have less data given to us. Part of it is that we already have a chemical formula, but we're only given an IR and a proton NMR. So because we have the chemical formula already, we can just calculate our degrees of unsaturation. So our DOU is equal to 2 times 11 carbons plus 2 minus the 14 hydrogens. Divide all that by 2. That should get us to 5 degrees of unsaturation. So quite a bit here, right? We should expect to see some pi bonds and rings. We have that, so let's go into our IR and see what we can find out. So one thing I will see right here is that it looks like, it's hard to see, this is the 3000 line. It looks like I might have only sp3CHs. Right? So in the IR here, I only have sp3CHs. I have a signal in the carbonyl region. This number here says 1693. I'll write that out here. So that is almost certainly a carbonyl. And then the other number that I have for a significant signal right here is this 1600 right here. So that's 1603. That almost certainly corresponds to some sort of an alkene. Right? It's a little bit too low to be a carbonyl. Looking at the proton NMR, I can go through and just, because I have the integrations here, I should just add these up just to make sure that it matches what I have in the chemical formula. It looks like I have 1 plus 2, 3, 5, 7, 9, 11, 14 hydrogens, so I don't need to worry about any sort of symmetry issue here. The 14 hydrogens in the formula matches the 14 right here. And then I should go through and count that I have 1, 2, 3, 4, 5, 6, 7 unique types of hydrogens. So 7 types. Now let's look at the chemical shifts of our signals and see what other information we can gain. I usually like to look from the downfield region first. So if I look over here, I see a signal at 10 ppm. That's very downfield, and almost always that's an aldehyde. Very characteristic. So I should kind of tabulate that over here, and I have an aldehyde. This would make sense given that we have a carbonyl. But one thing that's a little unusual is that the stretching frequency of the carbonyl is 1693 in the IR, but the normal stretching frequency of an aldehyde is more like 1725 or so. What that tells me then is that there's something affecting the carbonyl in this unknown structure that causes its frequency of stretching to be lower. Right? So that's something to keep in mind. This is not a normal aldehyde. As I continue looking in my NMR spectrum, so I can go now to this 7 to 8 ppm region. This is almost always an aromatic CH region. So that's almost always indicative of benzene ring of some sort. In this case, the pattern is that there's a 2H and 2H. So that means that two of the hydrogens around this benzene ring are symmetric, and then the other two are also symmetric. The only way to get that in a benzene ring is to have two groups to attach to the benzene ring, right? Because that leaves 4 hydrogens left. And to attach those two groups kind of para to each other around the benzene ring so that there's symmetry left and right. One strange thing here that you'll notice is that the IR had told us that maybe there weren't any sp2CHs, whereas all of the data points to there being a benzene ring with its CH present. And the way we can kind of rationalize what's going on is that because of the symmetry of the substituents around the benzene ring, that's probably just lowering the dipole change when you do your CH stretching. And because of all that, then maybe we just have less intensity of signal. So it is a little bit inconsistent, but there is no disputing from the proton and carbon NMR that there it's going to be an sp2 carbon CH bond. Beyond that, I notice I have a signal here at 4 ppm. That's usually some sort of a proton that's on a carbon that's next to an electronegative atom, often an oxygen here. Finally, I have a signal around 1 ppm. That's usually a methyl group, and that makes sense because I have this 3 hydrogen integration. And when I have signals around 1.5 ppm that are integrating for 2H, these are CH2s usually kind of in the molecule. So CH2, CH2. So that's a lot of pieces already right there. Let's go and see where we are in terms of our degrees of unsaturation. So we were supposed to have 5 degrees of unsaturation. It looks like I've identified the aldehyde as having 1 pi bond, so that's 1. There's a benzene ring, that's 4 more, that's 5. Right? So we're all set. The rest of our molecule should just be a chain. So basically, if I'm trying to attach 2 groups onto this benzene ring, I need to figure out now what those 2 groups are. Is it the aldehyde? Is it a carbon with an electronegative atom? Is it the electronegative atom itself? Or is it the carbon chain like this? One thing I do know is that I need a methyl group at the end of a chain. The methyl group is coming in at a pretty typical chemical shift, so this should not be directly attached to a benzene ring. Otherwise, this would have more anisotropy experienced and be more downfield. At this point, you really want to look for other clues as to what's affecting anything. And so the big one is that the stretching frequency of the carbonyl is so much lower. And one reason that that stretching frequency can be lower is because of conjugation with that aldehyde. So let's say our aldehyde was conjugated. Well, the only way to do that would be to attach it directly to the benzene ring, right? So I'm going to go through and make that my first guess. And I'm starting off with what's called a benzaldehyde, and I'm missing what's over here. The hard part here is to figure out, of course, what's attached here. So at this point, I've already taken care of the downfield region of the NMR, right? I have the 1H from the aldehyde, the 2H's from the aromatic ring here. Now I need to figure out where all of this is coming from. So if you're looking at the signals here, they are all split into more complicated splitting patterns. What that tells us is that all of these are likely to have 3J couplings. And what that means is then that all of the carbons that are attached to these hydrogens are just going to be all attached in a row. It's not really possible for us to have a situation like this because I would expect to have right here likely a singlet because these would have no 3J coupling constants, whereas only these would. And if these had no 3J coupling constants, I would expect to see a singlet up in the data here, and I don't. Right? So this cannot be the possible type of pattern that we're thinking of. So we should go through and figure out the splitting pattern. Looks like the 4.0 ppm signal, that's a triplet. The 1.0 ppm signal is also a triplet. It's a little hard to see what's going on here, but it looks like 1, 2, 3, 4, 5 lines maybe. 1, 2, 3, 4, 5, 6 lines. Right? So if it's 5 lines, that should be a pentet. If it's 6 lines, that should be a sextet. I'm going to call it sextet just to make sure it's 6. And from that, I think we can start to get a little bit of info. So whichever 2 hydrogens are attached to an electronegative atom, why don't I start building from that as my fragment? So I have a carbon, 2 hydrogens there, coming from this signal. That's going to be attached to an electronegative atom. It's also going to be attached to, because of the splitting pattern here, I know this is attached to a carbon with 2 hydrogens on it. So for now, I'll just code these as the blue shade here. These 2 hydrogens could come from 2 possible signals, right? It could either come from this signal right here, or it could come from the other signal that integrates for 2H, right? It can't come from this signal because this signal integrates for 3H, and I know that I need to have 2 hydrogens here. The way I can tell these apart is that they have different splitting patterns themselves. So let's say I were to think or guess that the right signal is responsible for these 2 hydrogens here. The signal here is a sextet, which means that there are 5 neighbors. So in order for this pair of blue hydrogens here to have 5 neighbors, it would need the 2 on the left in addition to 3 on the right. The problem with that now is that I've kind of run out of options here, right? I already said that I can't have a carbon, CH2, isolated on one side of an electronegative atom, right? I already said that. And so I can't kind of end my chain here because I'm not able to account for one of these signals now. So I should not put this CH3 right here. I should not account for this pair of hydrogens as being the signal at 1.5 ppm. So what I should do then is I will erase all this. And because of process of elimination, that tells me that this signal right here is probably the one that is corresponding to this pair of hydrogens. And because of that, then I know that this pair of hydrogens has 4 neighbors, which allows me to get to the pentet pattern. So I can fill that in now, 2 more neighbors. I know that these 2 neighbors should be from this signal by process of elimination. And now if I look at this signal, I need those 5 neighbors. I have the 2 blue ones and then the 3 from the methyl group that I haven't drawn in here. So that should now make sense. Cool. So finally, I should just fill in my electronegative atom, which is the oxygen, because there's nothing else in our chemical formula. This oxygen needs to have something else attached to it. The benzene ring up here needs something else attached to it. That seems to be a perfect match. Right? So then I can create a bond where those 2 dotted lines are to make my molecule. Right? And then I am all set. So the unknown molecule that corresponds to this data is this 4-butyloxy benzaldehyde compound.